Szanowni Państwo, ladies and gentlemen, the year 1676 was a very important year for the humanity because in this year new particles have been discovered. And particles which were not predicted by any theories of that time. What is important, they were discovered not by big collaboration like Atlas or CMS, but by a single person and in addition an amateur. And I'm talking about the discovery of the micro-universe by Van Leeuwenhoek. He had very good technology and he was the first person who saw something with this technology which one could not see with the naked eye. He built these microscopes and one day he saw something moving. People didn't believe him that there was something, but eventually he won. He would get Nobel Prize if there was one, but he didn't. Now he had some followers. Now he was not a very nice person because he didn't tell community how he built these microscopes. And if you look here, it took some time before people started competing with him, and this, of course, direction was very important for the medicine. Now, I will be using it as a starting point of a journey to very short distance scales. And over the years, people discovered nano-universe. I have nanotechnologists in Munich, very famous one, and they are very proud that they work with such small distances. But this is completely nothing compared with distances which we are studying in, going through femto-universe, atto-universe. And this is something what we are still exploring, but we are trying to go further, either directly, what Halina was talking about, through high-energy collisions. What you can reach there is something like 5 times 10 to minus 20 meters. And I don't think we will reach it before I will get 100, and this is this year. And therefore I'm going another route to find out what is there. And this is through very precise measurements, where through quantum effects you can learn something about much shorter distances, and this will be the main topic of this. And maybe I hope that I will reach one day this distance. This is so-called Zeptouniverse. So this is an expedition some kind from atto-universe to Zeptouniverse. And here is the base camp. This is my group. I'm sitting here looking at Bavarian Alps. It's very nice. And working here in this window. And this is this institute. And I got some money from European Council. And the overture is now finished. I to pozwala mi podziękować bardzo za zaproszenie. I chciałem Państwu powiedzieć, że to jest pewna rocznica dla mnie, bo ja byłem już raz, 2 razy już byłem na takim zjeździe. Pierwszy raz w 1967 ja siedziałem jako student w audytorium, a mój ojciec miał referat, profesor Bronisław Buras, starsza generacja zna go nawet z podręczników. I byłem też 10 lat temu w Szczecinie, gdzie dostałem ten medal z Smoluchowskiego Warburga. I mam nadzieję, że mój referat będzie na tyle dobry, że zostanę zaproszony za 10 lat. Overture is finished, and definitely you can expect what will come now. And there will come Wrocław Symphony number 15 in 4 movements. And the first movement will be some kind of excursion to the standard model for those who are not working in the field. Then I will tell you how I indeed, with some methods, can reach Zeptouniverse. This is what I hope. This is being developed. Then I will tell you what Halina already announced, that we are already seeing maybe something moving, some new particles, some new animalcula. And then I will be, already now you can see, very optimistic. Now, first movement. So this is the 2 pillars of our field, Heisenberg and Einstein. Heisenberg is very important here because it tells us that if I want to really look at very short distance scale, I need a very big momentum transfer energy, and Einstein is important anyway. I should tell you that my grandson, 3 years old, likes this photo very much. Whenever he looks at this, he says, "Oh, that's you, Grandpa." Yeah, okay. Now, everything is based on relativistic quantum field theory. There are very big names. what one should stress that the language which we are using is completely different than on the street, simply because the distance scales, energy scales, and time scales are very, very different. So we need a new language. Now, so let me stress again the frontiers of elementary particles, really looking at short distance scales as far as we can. At the moment, if you look, you want to test Zeptouniverse, units energies of 200 GeV, roughly. And here you have LHC, maybe we will reach this distance scales. That, as I told you, I don't think, I mean, Halina is optimistic, but I don't think there will be money to build such a collider to reach Zeptouniverse in 2046, and therefore I'm going the different route. You don't need high energy, but you need very high precision and many observables, as you will see, both from the point of view of theory and experiment. And this is the language, maybe I skip to save time, the dictionary between scales and energies. This is, again, something what you have seen. I will talk about it in more detail in a moment. We have quarks, we have leptons, and as already stated, the masses do not come from Higgs, which was discovered of neutron and proton, but masses of elementary particles. So this is a beautiful table. And let us look at this table from a slightly different point of view to define for non-experts what all these flavors are. And I have here neutrino family, I have electron family, and I have here up quark, jump quark, top quark, down quark, strange quark, bottom. Colors are related to quantum numbers of the strong interactions. And here I have this three generation. First generation, second, third, and we know already there is no fourth generation of the type. This is through study of the Higgs particle. And the flavors are these ones, different names for different quarks. And the thing which is very important, not really fully understood, is that if you look at one row here, at one family, all these particles can be distinguished only by their mass. From the point of view of quantum numbers, they have the same quantum numbers as far as standard model is concerned. And as you can see, there's fantastic hierarchy, which we really do not understand. So this is a very important issue still to be understood. So these masses are measured and enter various calculations. And these calculations are based on Feynman diagrams, which are also known in other fields. And here, for instance, there's Z plus E minus collider, there's gamma, Z, there's some production mu plus mu minus. Here may be more important for me, or maybe even this, is the big quark, there's jump quark, there's some, for a very fraction of seconds, these are really 10 to minus 23 seconds, there is a W exchange for a moment, and then there is something. So these are vertices, propagators. You can draw more complicated diagrams. I will show you one or two, but I will not, of course, do calculations here. And the basic thing which I will be using at the end, really to see what happens, are the probabilities for certain things to occur. What these things to occur is, I will define in a moment. So we have this fantastic framework, which was already shown here many times, so I will not really discuss it here, but we have quantum chromodynamics, this quantum flavor dynamics, what I call standard model electroweak interaction in QED. And this is really framework which is based on very important concepts. And this is our world form. For somebody on the street, it's our hieroglyphs. I mean, you don't know what it is, there's some drawings, whatever. But of course, we know what to do. We know how to calculate things from this. There are still open questions. One, this is more for people from statistical physics. This is we are at the level really of Ginzburg-Landau theory from spontaneous symmetry breaking. This is the sector of the Higgs. And the other issue is important. This is related to the mass. Otherwise, don't worry, I will not use this formula at all, just to show you we have this formula and we can do things. Now, let me now recall certain properties which are very important for this talk. And one is that these particles cannot change flavor. So this is zero. This is flavor I, J. So up, they cannot change flavor. They could go from up to jump, but they cannot. And they conserve parity, charge conjugation, CP parity, all these symmetries. This is so-called Glashow-Filiopius-Majani mechanism. And the only particle which does all the things, violate charge conjugation, parity, and so on, in the standard model, and actually the only one we know, is this charge boson. So it can really change the flavor. And another very important property, interacts only with left-handed quarks. I mean, usually fermions have left and right hands, but this guy interacts only with left-handed ones. And the second thing is that all these couplings here are universal. They're exactly the same. You have different particles, similarly for this thing. And as I'm telling you because later we will see some signs that maybe there is something new. And we have this universal coupling. So these are these 4 properties. And the important point is, and this is again with this W boson, is that this interaction is not as simple that there is a number here. There is a matrix of numbers which tells you simply how, what is the strength of certain interaction from U to D, jump to S, top to bottom, or like that. And you can see it's almost diagonal. It's very close to 1. And on the corners, you have certain elements which have complex phases because this matrix is unitary. And as you can see, the phases are not small. But the problem is that the coefficients here are very small. And therefore, we cannot explain matter-antimatter asymmetry in the standard model simply because these effects are small. And this is not the only effect, as well known. But this is one of the effects. Now, I want you, there are more complicated diagrams. Here are some of them, which through some constructions can still produce certain transition which Z could not, W plus, W minus. And the most important thing for this transparency are the names. As you can see, here I have box diagrams, and they look really like boxes. Here are other diagrams, which also can produce something, transitions of the type. I will be mainly talking about such transitions here. This is just transition. You don't have to know exactly what it is. And they are called penguin diagrams. And you can probably disagree with me because a penguin diagram does not look like penguin. But you should realize that the Feynman diagrams do not look like Feynman either. So this is really not a problem. But if you start looking and reading papers and books about Feynman, you can see that my last statement was indeed wrong. So the standard model really works very well. And on the whole describes the phenomena like Halina already said. But there are very important questions which we still have to answer. And this is, are there any other elementary particles? What is the origin of vast difference? Because all these masses, neutrinos are almost massless, top is rather heavy. We do not really understand why neutron is heavier than the proton. If it was opposite, this talk would not take place, and maybe it was better. But the other questions are very important. Is why is our universe dominated by matter, dark matter, the issue of dark matter, and so on and so on. And none of these questions can be answered within the standard model, and this simply means we have to go beyond. And if Halina cannot find new particles, I will find them. And this is going through this different route. So the basic questions for the next minutes, let's see how it goes, is can we, with this technique, really go to 100 TeV and see what is going there? So this is basically what I will go, and this is second movement. The main actors here are not protons and electrons and so on, but these bound states of quarks, B mesons and K mesons, and there are some others. This, as you see, they do not have the masses. They are produced, really, this is what I need, definitely Halina, they are produced in milliards in a collider, and then they simply decay. We call it decay. This is not classical decay, but simply they go to other particles through quantum effects. And the main thing what we measure at the end, the probabilities with which these decays occur. And by looking at various structure, which I will illustrate in a moment, we can maybe learn something what happens at very short distance scales. So let me now show you one example. This is only to illustrate what's going on. I have here this bound state of quarks, P+, and I have W, and it ends like that. This is a process I can calculate within the standard model, and I get a probability for this to occur. There are some maybe coefficients. There is this propagator, 1 over mw squared, and I know it. Now let's assume there is another particle, which I don't know, I didn't discover it yet, which is very heavy. And it can be also exchanged, because it happens really very shortly. I don't need this energy, just for microseconds, not microseconds, but short time. And it also contributes to this decay. Now, according to quantum rules, I have to add them. There could be an interference. And if experiment tells me that the measurement of the probability for this decay is different from the standard model, I know something happened there. And this is how I can learn it. So now let me go to 2013 and tell you something more explicit. So we have this P-sub-S method, and we can ask yourself, how can it be transformed to two muons? I mean, there's a quarks, there's a muons, and so on. There is some interactions here, some quantum fluctuations, and we try to look at the probability and see what it is. I can answer this question in the standard model. So this is one diagram. As you can see, the probability will not be very large, because here are all these weak couplings. There is stop, there is W, very complicated, because I cannot go through the boson directly. I have to construct something. So now the question is, what is the probability for these things to occur? And the first calculation, correct one, was done by us in Munich, by my student Buchala, who is now professor not only because of this calculation at LMU in Munich, and we found at that time still not very precise result, because top quark mass was not known, given here. So 3 and so on. So you can see, you produce 1 milliard of these guys, and only 3 of them go into two muons. And these calculations were improved over the years. Also, Mikołaj Misiak from Warsaw was involved. And this is what we have at the moment, 3.65, with slight improvement last week by some people in Munich. And so people knew it already for quite some time. And therefore, it was clear. There must be new physics which will completely change the prediction. And people were looking until 2010, supersymmetry. There will be 10, 100 of all this decaying into two muons. Then people got modest. I was working with also Stefan Pokorski. And in January 2013, we had from some theories calculation that maybe it will be 5. And then came EPS meeting, 2013, July. I was sitting in audience. This has been seen. The decay has been seen, as you can see. So I was saying, oh, there will become 5, 7, 3. So people congratulated me, because it was 20 years after we did this calculation, but I was really depressed, because this was mean that here we will really have a very hard time to find something. But the point is that, first of all, the data have to be improved. Maybe, hopefully, this number will go down and we will have something. But the point is that there is no way, on the basis of one transition, to tell you what it is. So you really have to look at very many decays. And this is why I'm so optimistic that there are very many coming now. In a few years, we will have most of them, all these probabilities. And so to stress it, you need many precision measurements, study patterns of various probabilities. I will illustrate in a moment, some correlation between them. You need a very good theory. And so this is really very important. So let me now show you what is really the basic idea to get it. So I work, first of all, 20 hours, and I look at various transitions. These are, like chemistry, there are some transitions governed by some fluctuations. So this is one thing. I have to measure many of these probabilities related to it. And I have many models, whatever they are. I cannot discuss them. There are some theories. There are many theories that construct this model with new particles and so on. And I want now to test it. And what I do, the idea to get first idea what it is the following. A given theory will modify the probabilities with the standard model. It can go up. Maybe it will be no modification. We have to quantify how. And maybe it will decrease. So now what I will do, in a moment I show you, I go to one of these models and have a look here how in these models all these processes are affected. So I go, this one theory, second theory, third theory, fourth theory, fifth theory. I can continue forever. But the main point that this is some kind of DNA where you can really, some theories immediately by comparing with experiment was, and I tell you what is now, really decide what it is. So let me now move to the third movement. The last one will be very short. We indeed see some signs of new physics. And there is in BT case, and there is a very big excitement, which can be compared to climbing of the Mount Everest. And really, there are very many papers. This is in B physics, in the case of these B mesons. But there's another field, K mesons, and this is, to be compared with this, like hiking in Norway. There is nobody there. Your wife is taking photo of you, and you can go slowly sing and produce paper. There is not much competition, and this is very good. I will come to this in a moment. But this is the reaction of a community for all these so-called B-physics anomalies, hints for new physics. And I, of course, cannot go into details, but the point is that precisely certain probabilities for this decay have been measured by LHCb, by Bell, by Babar, various, and as you can see, there are really certain deviations here. And so this is the standard model here. Here are the data. As you can see, there are really differences. This is interesting. You would expect something like unity. In the standard model, there is really deviations, other deviations, and so on. So this is something what people really think there is something there, because it's not only one transition. And you can see one of the plots for these ratios. This is the standard model. Here is some world average of various. And now that you could ask yourself, what could it be? And people wrote many papers, and the strongest candidates for this, which could explain maybe most of them, I will show you this DNA in a moment, is a new heavy boson, much heavier than neutral boson, but much heavier than Z, maybe 3 TeV, maybe 4 TeV. Another object is very interesting, so-called Klepto Quarks. This in standard model we do not have. This is a gauge boson. We can transfer a lepton into quark. So that's very interesting. This is very popular. This is graph. And there are so-called vector-like quarks, which then with two hands, so to speak, attacked weak interactions. So this is the situation. But there are the anomalies. One which is already going for a very long time, for 15 years, and this is so-called anomaly in the anomalous magnetic moment of the muon, this G minus 2½ This is 4 sigma. So this is one which hopefully soon will be answered because of Fermilab. There will be repetition of this Brookhaven experiment. But there is another anomaly which I'm pressing very strongly. And this is the one in CP violation, but in K system. And there are two types of CP violation. I cannot explain it here, but there is one so-called epsilon prime, already measured by experimentalists in 2000, but it's very difficult to calculate the prediction in the standard model. But the newest calculation, both by lattice gauge series, this is here the data, and this also used. As you can see, there is a difference not by 20%, by really, or maybe order of magnitude, order 5. And this is something what I did. I was also involved here. This is an upper bound. As you can see, this is much smaller. And this is what I claim. This is the largest anomaly in Flavour physics at the moment. People don't believe me, which is very good, because I got older, so I have no competition. But I'm sure in 2 years they will accept that this is the really new physics is found here. So let us now, because I have to close soon. So this is the what I could do. And I have not so many observables, but I could try drawing these DNA tables. And you can see that this is what experiment is telling me. I took only three of them, and here on this side are others variables, and I have plus, plus, minus, minus, plus, plus. This is what the nature is telling me. And now Klepto Quarks are doing pretty well, but fail. There will be a paper very soon on epsilon prime over epsilon. And this heavy Z has no chance to explain here, but is doing very well here, in particular epsilon prime. So the physics at the moment, you could say naively a bit, that it's maybe some Klepto Quarks and Z prime, but we really need much more data in order to identify and to be sure that the data we see are really correct. Now, my great love, there is another decay where I spent already 25 years looking at it, and these are the predictions where Mikołaj Misiak was also involved. And as you can see, these probabilities are even lower than what was the one where it was 3 times 10 to minus 9. And the fantastic thing is that in next year, we will know what it is. And I hope it will be 20 in these units, but maybe there will be again disappointment. Now, before I close, let me tell you, we did a study. You have to look. This it's not as simple as I was talking. Here there are really very difficult calculations. Mikołaj is a big expert, and we are doing many. And indeed, with this physics, you can learn something about Zeptouniverse, maybe even higher scales. So you can see LHC can do 4 TeV, but I can do here much bigger numbers. So I think this is the future. I hope Halina and colleagues will discover something, because this would also tell us for this work a bit which direction to go. But here I'm sure we will see something. So this is the main message of this talk, that this rare decays will play a very crucial role in identifying new physics, hopefully not only in Zeptouniverse, but on the way there. And the final thing is very brief. I think there are exciting times ahead of us. Coming years will bring not only improvements luminosity at CERN, but there will be in various directions also improvements theory, like improved lattice calculations and various measurements by experimentalists, which I believe, if I get invited in 2027, I will be able to tell you what is on the Zeptouniverse. And so this is the expedition, as I repeat. And I still push that Kayan physics, which play a very important role. As you can see, already anomalies have been found. Thank you very much.
Thank you very much for a very interesting talk. So I think we still have 1 minute or something like that for maybe one question, if I may. So
if I combine your interesting talk with equally interesting talk of Halina, let's assume that one of these mountains is the future experiments which we would like to choose, and you are staying there where you are. Which mountains you would choose now?
You are talking about
which
now.
You have now.
You are talking about.
I talk about FCC, ILC.
What Halina was talking about,
yeah,
not the precision measurements.
I mean.
Yeah,
that's your choice. Okay, would you like to stay on the same level?
No, I think there are enough people that I can do my work.
For the next 20 years to have better precision experiments, or you prefer rather to change the technology, the accelerator? You go to E plus E minus, or you go to the high energy PP collisions to verify your idea. If there is a new particle, I mean, you can of course look on the corrections of the vertices or some processes, but at the end of the day, you would like to discover this particle directly, and to see it, you have to go to high energy. There is no way.
I completely agree with you. I completely agree with you. The best thing, and this unfortunately, I hope that now, usually the way I'm doing was always ahead of, like Z and so on. And I still hope, Halina, that we have now the situation that we discover something in low energy processes and they discover at LHC, because there you can really make a correlation. Now, the thing is, I still believe, and this is probably what you wanted me to say, I still believe, even I will be not around, that we have to go to high energies. There is no question about it. And maybe the good idea is not to start with. And I would not go, sorry to say, to E plus minus collider or EP. I would really do proton-proton as high as I can. And maybe I would do, maybe not 100 TV. I think the idea is to double LHC. This maybe is a good idea. Maybe I still can see it. This is maybe egoistic a bit. But I definitely, no, the future is of course high energies. You have to see the particle. If you measure 100 processes, maybe you can say some things, it's completely rule out. I should stop. Something, I will be ruled out in a moment. Right. Now, something is ruled out and certain things, but eventually, you know, I completely agree. I mean, you have to go up.
Dziękuję bardzo.